Why is space dark? A deep dive into the cosmos. Space, the vast and seemingly endless expanse beyond Earth's atmosphere, is often depicted as a deep, pitch-black void sprinkled with stars. This visual emptiness raises a curious question. Why is space dark? After all, if space is full of stars emitting light, shouldn't the universe be filled with brightness instead of darkness? This enigma has perplexed scientists, philosophers, and astronomers for centuries. To understand why space is dark, we need to explore several key concepts in physics and astronomy: how light behaves, the nature of space, the limits of human perception, and the history of our understanding of the universe. This article will unravel these layers and provide a comprehensive answer. The nature of light and vision. To begin, it's essential to understand how light interacts with our eyes and the environment. Light, which travels in the form of electromagnetic waves, enables us to see objects when it reflects off them or is emitted by them. Here's a simple breakdown. Objects on Earth are visible because they reflect light from sources like the sun or artificial lights. These light waves bounce off surfaces and travel to our eyes, where they are processed by our retinas, creating the sensation of sight. In space, there is no atmosphere or medium to scatter light as there is on Earth. This absence of scattering is a key reason for the darkness. Light from the sun and stars travels in straight lines and doesn't illuminate the vast stretches of space uniformly. The reason space looks dark to our eyes, despite the presence of countless stars, has to do with how light behaves in the vacuum of space and how our vision works. We see light only when it hits something, like planets, moons, or spaceships, or when it enters our eyes directly. Most of space is empty, so there is nothing for the light to reflect off, giving the appearance of darkness. The vacuum of space, lack of scattering. On Earth, our atmosphere scatters sunlight, especially at shorter wavelengths like blue and violet, making the sky appear blue during the day. This process, known as Rayleigh scattering, is absent in space. Space is a vacuum, devoid of air, particles, and gases that can scatter light in the way Earth's atmosphere does. Because there is no medium to diffuse sunlight, light travels in a straight line through space. We only see the light from a star if we look directly at it. All other areas between the stars remain dark because there is nothing to reflect or scatter that light toward us. Olber's paradox: shouldn't the night sky be bright? One of the earliest questions about the darkness of space came from a German astronomer named Heinrich Wilhelm Olbers in 1823. His paradox asked why, if the universe is infinite and filled with stars, the night sky isn't completely bright. If there are stars in every direction, shouldn't their light fill the sky? Here's how Olber's paradox can be visualized. Imagine a dense forest where, in every direction, there's a tree. You'd expect that when you look around, all you would see are trees. Similarly, if the universe is filled with stars in every direction, the sky should be ablaze with their light. The resolution to Olber's paradox lies in the understanding of the finite age and expansion of the universe. 1. The universe has a beginning. The universe isn't infinite in time. It began with the Big Bang approximately 13.8 billion years ago. This means that the light from stars that are too far away hasn't had enough time to reach us yet. The observable universe is limited by the speed of light and the age of the universe. So, we only see stars within a certain distance, and beyond that, space remains dark. 2. The expansion of the universe. As the universe expands, distant galaxies and stars are moving away from us. The light from these distant objects is redshifted, meaning its wavelength is stretched and shifted toward the red, less energetic end of the spectrum. In extreme cases, this redshift moves the light beyond the visible spectrum, making it invisible to human eyes. The farther away a star or galaxy is, the more its light is shifted, until it fades from our view entirely. Cosmic microwave background radiation, remnants of the Big Bang. While space appears dark to our eyes, it's not entirely devoid of radiation. After the Big Bang, the universe was filled with extremely hot and dense energy. As the universe expanded, this energy cooled and stretched, resulting in the cosmic microwave background (CMB) radiation, a faint glow of energy that fills the universe. However, the CMB is not visible to the human eye, as it exists in the microwave part of the electromagnetic spectrum. It is a relic of the early universe, detectable with sensitive instruments, but it doesn't contribute to the visible light that illuminates space. Our eyes and the limits of human perception. The darkness of space is also partially a product of the way human vision works. Our eyes are sensitive to a narrow range of the electromagnetic spectrum, primarily the visible light spectrum, between 400 and 700 nanometers. Many forms of light and radiation exist beyond these wavelengths, including infrared, ultraviolet, X-rays, and gamma rays, but they are invisible to us. While telescopes designed to capture these wavelengths reveal an active, dynamic universe filled with radiation and energy, we don't perceive that with our naked eyes. To us, the absence of visible light results in darkness, the absorption of light by dust and gas. Though space is mostly a vacuum, there are vast clouds of dust and gas spread across the universe. These interstellar clouds can absorb or block light from distant stars and galaxies, further contributing to the darkness we observe. Some regions of space, especially areas with thick nebulae, can block out starlight entirely, appearing as dark patches even in areas populated by stars. Conclusion: darkness as a fundamental aspect of the cosmos. Space is dark because of the complex interplay between light, the nature of the universe, and the limitations of our perception. While space is filled with stars and galaxies emitting light, the vast emptiness between these objects, combined with the lack of atmospheric scattering, the finite age of the universe, and the expansion of space, results in the apparent darkness we observe. Moreover, much of the light in the universe is either outside the range of human vision or absorbed by cosmic dust and gas. While the darkness of space might seem puzzling, it's a natural consequence of the laws of physics governing light, the universe's structure, and our biological limitations. In the grand scheme of things, this darkness is a reminder of how small our perspective is in an incomprehensibly vast and dynamic universe. Understanding the darkness of space not only deepens our appreciation for the cosmos but also highlights the mysteries that still remain as we explore the final frontier.